Happy Friday. This is the part where you also say Happy Friday. All right. To emphasize that, let the record show, they said they've acknowledged it is Friday. The debatable part was the happy part. It's Friday. Ouch. Tough crowd today. This is next chapter. This one starts by reviewing average rate of change versus instant rate of change. We've already talked about this a little bit, but it's worth going over again because it's a huge part. So average rate of change, abbreviated AROC. What is that doing? What? There we go. Average rate of change. I'm just going to draw a generic little polynomial here. When I'm asking for an average rate of change, it is very much like an algebra 1 slope problem. Okay? Okay? Do you remember what type of line that's called? Starts with an S. Secant. I heard it. Secant line. And if they said something else, that's fine. It's a secant line. Secant line, you might have known it from geometry, you might not have. But it means it's crossing twice. Average rate of change from X to C would be that. Okay? So, slope of the average rate of change would be slope of a secant line, f of x minus f of c over x minus c. Or if you remember algebra 1, stuff like that. Or change delta y over delta x. Those are all ways you can talk about slope or an average rate of change. Okay, so average rate of change is very much an algebra problem versus instant rate of change is a calculus problem. Where we'd see it's not going to be that secant line, and we redefine it a bit. I don't love that. That's almost the same. But it's going to be tangent line. So I can say something like, I'm going to redefine this a different way. Where you still have your point x, and we did all this work on limits for this. So if I have this point x right here, and some distance h, make that look like an h, x, some distance h, and then a second point x plus h. We get a limit of that f of x plus h, take away f of x over h. The whole point of doing a month's worth of limits was this instant rate of change. Because what this is saying, f of x plus h, take away f of x, and this distance, you want that distance to slowly get to 0 so that it would get some type of instant rate of change, where it's going to just barely touch. Okay? And I have an alternate definition worth writing, but I'm going to only touch on this, like have a definition here, and then we'll talk about that later. Limit as x goes to c. I'll talk more about alternate definition on another day. This is just notes, definitions. This is not the actual application yet. So, do you need to zoom in? Okay. So consider this right here, this graph, all it is, that's the graph x squared. You know, if I extended it, it would look like that parabola right there. So consider average rate of change on the interval 0 to 2. Average rate of change, f of x minus f of c, so whatever, this could be x, 0 to c, whatever. Slope, 0 squared minus 2 squared over 0 minus 2. Zero squared is 0, 2 squared is 4, so 0 minus 4 is negative 4. 0 minus 2 is negative 2. Negative 4 over negative 2 is 2. Say what? You good? So graphically, what does that look like? It's an average rate of change. So on average, from 0 to 2, it would look like that. That is the specific secant line if you're going on the interval from 0 to 2. What's that? Straight edge. Straight edge. I definitely used a book of passes on that one. Or yeah, I probably could have done. Nope, that would not have been cool. Yeah, but like use your ID or something. Average rate of change from 0 to 2 is that slope 2. Now, changing up the interval to get closer to an instant, I'm now going to look at the interval from 1 to 2. So, got 1 squared minus 2 squared over 1 minus 2. 1 squared is 1, 2 squared is 4. 1 minus 4 is negative 3. 1 minus 2 is negative 1. I'm sorry, that should be a positive 3. Finding just the slopes. So, from the interval 1 to 2, slope 3. Now, does that kind of make sense? Because as we're looking at these intervals, is it more steep here, or from 1 to 2? Is it growing faster? It should. So like if I'm looking from only 1 to 2, my interval on 1 to 2, average rate of change is 3. And you can tell it's a little bit steeper because the graph is climbing faster. Are we at an instant rate of change yet? Hint, say no. No, we're looking, this is still an average rate between, on an interval, between 1 and 2. So make the interval smaller. I'm going to go to Desmos for this. This next one is 1.9 to 2. So now we're getting a really small interval. So 1.9 squared minus 2 squared over 1.9 minus 2. Okay, so I'll change my color. Let's go purple on this one. 1.9 squared minus 2 squared over 1.9 minus 2. We see is 3.9, right? So again, looking at the graph. So where's 1.9? Well, 1.2, 1.4, 1.6, 1.8. So we're really looking at 1.9 would be like right here to there. That type of interval, it's getting really, really close, zoomed in now, right? So it's getting closer and closer and closer to that instant rate of change as that interval gets very, very small. Huh? Where did I draw the blue line at? Interval from 1 to 2. Blue line was 1 to 2. Purple line was 1.9 to 2. Was there another question out there? So it's getting closer and closer to instant. And that was slope 3.9. All right, and then these next two, I'll just go back to Desmos on that. 1.99 is going to give me slope 3.99. And what do you think this next one's going to be? 3.999. So you know a little bit about limits now. All of these were average rates of change. I tried to make that distance between the intervals very, very small, but there was distance between the intervals. Here, there was 2 between, 1 between, 1/10 between, 1/100th between, 1,000th between. So these are intervals, but they're getting very, very, very small, and these slopes are getting very, very close to instantaneous rate of change. What limit do you think this is going to? 2, 3, 3.9, 3.99, 3.999. These are all approaching 4. The average rate of change gave us a bunch of ideas of what it could get close to. Instant rate of change is the limit. It's 4. You will have to recreate that with a different function on delta math. Okay? So the other way to do this is by definition. So using this definition right here, f of x plus h, or f of x is x squared. So if I apply that, by definition, f of x plus h would be x plus h quantity squared minus x squared over h. Yeah, remember this? let the video show that some people are nodding like, yeah. Not happy I remember it, but. Also, x plus h squared is x squared plus 2xh plus h squared. It is not x squared plus h squared. Some unfortunate kittens. There's that minus that. Please speak now if you don't know where I got something. Okay. Some stuff simplifies, and we'll have 2xh plus h squared over h. And then I can factor out an h. Factor out an h. There, I got it this time. 2x plus h over h. And it simplifies to 2x plus h. Just a little bit more magic in this one. So bring that back on over, because this is a limit as h goes to 0 of 2x plus h, but then essentially you plug in that 0 to get 2x. And you're probably wondering, like, I still don't see it all come together, right? But we wanted the limit as x goes to 2, right? By definition, all of this algebra, whereas before we could just set up the table and look at that limit. You could do it by table and looking at what the limit approaches, the table and look at what the limit approaches, or by definition, that's a whole lot of algebra. All right, so let me see here. Let me end the video. Do you want to say bye?
Bye.